All right, welcome to the review of Chapter 7. Make sure you have a paper, pencil, and a book in front of you before you start. Pause the video now to make sure you've got those things in front of you. Pause the video now to make sure you've got those things in front of you. Paper, pencil, book. Chapter 7 is a review of the periodic table. We're going to take a look at a lot of trends on the periodic table, where the electrons are for various atoms. So having a periodic table in front of you is helpful as well. Pause the video now to make sure you have a paper, pencil, book, copy of the periodic table in front of you. All right, first thing, electron configuration. This is actually a carryover from Chapter 6, but knowing where the electrons are around the nucleus of an atom is key to understanding how atoms will act. Remember that the electron configuration is pronounced 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then it goes 3d10, and then 4p6, and then 5s2, and then after that it's 4d10. So watch out for that and know how your periodic table is organized, that these guys right here are the S's, these guys right here are the D's, and remember that the periods numbered 1, 2, 3, 4, 5, 6, 7 apply to the S's, but they're -1 for the D's. Remember, these are the P's right in here, except for helium. Remember, that's still part of the S's and actually belongs over here when you're doing this. And then these guys down here are the Fun and Frankensteins, and remember, these are -2 and fit right in here with the lanthanum and actinium series, and these are called the rare earth metals. Be able to count and find this. It'll show up. I'll show you a bunch of examples from the past couple of years where you end up writing some type of electron configuration with a crappy periodic table in front of you. We're going to look at 6 different trends. We're going to look at trends on the periodic table that form what are called effective nuclear charge, atomic radius or size, radii of ions, ionization energy, electron affinity, and electronegativity. I'm going to explain them super briefly, point out in your textbook where they are, and then if you review them a little bit more, you can look at them. You can look at them. Okay, got those written down? Pause the video now if you need to. Section 7.2, effective nuclear charge. What this is the amount of attraction the nucleus has for an electron. The amount of attraction the nucleus has for an electron. The closer the electron is to the positive protons, the more effective nuclear charge it has. The further the electrons are away, the more trouble the nucleus has attracting the electrons way out here. So the further away they are, the less effective nuclear charge the electron sees or views or feels. Generally, for every 1 proton, there's 1 electron, so we say it's a 1-to-1 effective nuclear charge. But if there's lots of electrons in the way, called the screening or shielding effect, now it's not a 1-to-1 ratio anymore, it's a little bit less. Effective nuclear charge can be used to explain all trends on the periodic table. 7.3, atomic trend of radii. Radii, remember, is atomic size. And if you look on page 266 of the 10th edition of Brownell Burston, they have a really nice graph here of how atomic radius changes across the periodic table. Notice radius increases to the left, and it increases as you go down. It increases to the left because there are less protons in the nucleus. It increases down because you add actual shells of electrons. You need not only to memorize the trend, but why the trend occurs. Radius is actually defined as the bonded atomic radius, and you should know the difference between bonded and non-bonded atomic radii there on page 266. Okay? 7.3 also talks about trends of radii, radii, 2 I's, 1 D, radii of ions, okay? And when an atom becomes an ion, it gains or loses electrons. So if there's an atom, I'll just put A right here, and it gains an electron, has an extra electron, you can understand that the size would get bigger. Gains electrons equals bigger, okay? If there's an atom, we'll call it A, and it loses an electron, then we say that the atom gets smaller, okay? Now remember, when it gains an electron, it becomes more negative because electrons are negative. When it loses an electron, it becomes positive. Remember the joke? 2 atoms walking down the street. One said, "I think I lost my electron." The other one says, Are you sure? And the other one says, yes, I'm positive, because he lost an electron. So you can see right here, here's the trend of radii. Fluorine going from F to F minus got bigger because it gained an electron. Lithium going from Li to Li plus lost an electron, so it got smaller, and it's one of those pink colored ones. This is on page 269 of the 10th edition of Brown-Lemay-Burston. Okay? Next trend in section 7.4 is called ionization energy. Ionization energy. The ionization energy of an atom or ion is the minimum energy, measured usually in kilojoules, required to remove an electron from the ground state of the isolated gaseous atom or ion. Notice it's got to be in a gaseous form. The first ionization energy, usually symbolized I1, is the energy needed to remove the first electron from a neutral gaseous atom. The second ionization energy would be the energy needed to remove a second electron, and so forth. Knowing the equation for ionization energy is many times critical to an easy point question. So for example, Na gas going to Na plus 1 gas plus an electron would be the equation for the first ionization energy of sodium. Na plus gas going to Na gas plus an electron would be an equation for the second ionization energy. Notice it's gaseous. Notice it's losing an electron, so the electron's on the right-hand side or product side. You can see right here is a nice little graph or table of the successive values of ionization energies for the elements sodium through argon, which is period 3 on the periodic table. And you can see that the second ionization energy is always larger than the first. And then they have a blue line right here where the ionization energy takes a quantum leap or jumps a lot. It goes from 495 to 4,000, from 1,400 to 7,700, from 2,700 to 11,000, from 4,000 to 16,000. What happens at this line? This is the point at which an atom is right at this point right here. It's at the point of looking like at the point of looking like a noble gas, and it wants to stay looking like the noble gas. If it loses another electron, it's going to have an electron configuration that's much like a halogen. It's very, very difficult to remove another electron once it gets to that point. You can identify an element by looking at that, and we'll see there was an AP question like that very recently. You should know your trend in ionization energies. Your trend in ionization energy, just by looking at a mini periodic table here, is ionization energy increases up and it increases to the right. There's more protons in the nucleus here. Electrons are closer to the nucleus, and therefore they experience greater effective nuclear charge. Okay? You can use that trend from the beginning of the chapter to help explain that one. Let's see. They've got a nice trend in first ionization energies right here on page 273 of your text, 10th edition. And then they also point out some of the anomalies here in this picture on page 272. It's very interesting to see that actually the ionization energies at several points along the periodic table aren't a simple, easy trend. Like it takes a little bit more energy to remove an electron from magnesium than it does for aluminum, where we said atomic ionization energy increased to the right. Well, it's a little bit more difficult because we have some paired electrons there too. It's 3s2, whereas this one is 3s2p1. It's easier to remove that one because it's in a shell by itself. For example, right here, this nitrogen and phosphorus guys right here, they have a 3s2p3, and so if you draw their atomic orbitals here, it's got a half-filled orbital, which is fairly stable. So it's a little more difficult to remove that than it is from the sulfur. Those anomalies you should be able to deal with. Last trend. Oh no, there's two trends left. Electron affinity. Oh, backing up just a second. Electron affinity and ionization energy, I said, are both amounts of energy. And remember, the energy is in kilojoules. And the amount of energy needed to remove an electron in ionization energy is given in kilojoules per mole of that gaseous ion or that gaseous atom. And notice that it is always a positive value. Always a positive value because you have to put energy in to remove an electron. You have to put energy in to remove an electron, okay? Electron affinity, on the other hand, well, electron affinity is a little bit different. Electron affinity is usually the energy released when an electron is added or gained. Okay, when an electron is added or gained. You can see a general trend here. This is on page 276 of your text. And you can see in the general trend, and this one is not a very good trend at all, that electron affinity becomes more negative, more exothermic, as you move to the right, until you hit the noble gases. Noble gases, of course, have a positive electron affinity because they need energy put in to force them to gain an electron. You can see here that some of these need energy put into them to make them gain an electron too, because they have a filled, in this case 2s, in this case 3s sublevel. And you can see that actually the trend isn't very good because the nitrogen, the phosphorus, and the arsenic having half-filled p orbitals there don't really give off a lot of energy when they gain an electron either, because they're like pretty satisfied with a half-filled one. All right. The last one, not in chapter 7, but actually in chapter 8, but it's a trend, is the trend on the periodic table of electronegativity. Electronegativity is not an amount of energy in kilojoules per mole, whereas electron affinity and ionization energy are. Oh, backing up once again really quick to electron affinity. Remember, electron affinity, for example, argon gas plus an electron making argon negative charge right here, gas, is defined as the gaseous atom gaining an electron. So make sure you write that down. Make sure you write that down, because that's a trick question on multiple choice too, that they'll give you a bunch of equations and they'll say which one is the electron affinity of such and such. Make sure it's a gaseous atom, make sure it's gaining an electron, and then of course it has a more negative charge on the right hand side. Okay, trick question there. Electronegativity, remember, is a rating system of how much an atom wants to gain an electron. This is on page 312 of your textbook, and you know electron negativity increases up and to the right. And this is a nice little stable graph that shows you cesium is the lowest, fluorine is the highest. Notice it omits the noble gases, which of course would probably be the lowest because they don't have a want for electrons pretty much at all, since they don't react with very much of anything except for xenon, maybe a tiny bit of krypton. Electronegativity is just a rating scale, and it gives a numerical value right there. And electronegativity is defined as the ability of an atom in a molecule to attract an electron to itself. Notice it's in a molecule, it's not an atom by itself. Let's look at some problems from past AP exams. You can write down the years that used these chapter 7 type questions. Here's 2010, question number 6. Let's take a little closer look at some of these. Write that down, 2010, question number 6, because you'll probably want to come back to it. 2010, number 6. Okay, this is a chapter 7 type question. It also goes on to talk, loves to mix chapters. It asks a little bit about chapter 22. First, write the complete electron configuration for Zn plus 2. Notice they throw a twist in there. It's Zn plus 2. What does that mean? That means it lost 2 electrons. So write what zinc would be, okay, and then get rid of 2 electrons. Which electrons are usually lost? Remember, it's the s and p electrons from the highest energy level. So you'll see it would normally have a 4s2 in there. 4s2 in there. It doesn't, because it lost those 2 electrons. Okay? Which species, zinc or Zn plus 2, has the greater ionization energy? Justify your answer. Love that. Zn plus 2 has the greater ionization energy. The electron being removed from Zn plus 2 experiences a greater effective nuclear charge. Look at that. They use those words. Then the electron being removed from zinc, because Zn plus 2 has 2 fewer electrons shielding the nucleus. They even talk about shielding. What an amazing question. It takes more energy to remove negatively charged electron from a positive ion than a neutral atom, which makes sense too, because if it's Zn plus 2, it's already lost 2 electrons, right? So it has more protons in the nucleus than electrons that are available, so it's harder to remove it. Identify the species that is oxidizing the reaction. Up here they gave you an oxidation reduction reaction. They didn't tell you that. I didn't go through that, but now it goes into a chapter 4 type question. And then if you look on the back here, question 6 continues, and they give you like a whole bunch of stuff for electrochemical reaction. We'll hit that one again back in chapter 20. More chapter 7 stuff though. Here's a little table. Ionization energies, using the principle of the atomic molecular structure. Hey, this is 2008 question 5, write that down. 2008 question 5, okay? Write the equation for the ionization energy. Told you they'd ask you to write the equation. Ionization, okay? F loses an electron, so then it becomes positive. Remember, I lost an electron, so it's F plus 1 right there. Make sure that it says phase designations are not required, but make sure that you'd put in that gaseous right there just in case. Account for the fact that the first ionization of fluorine is greater than the atomic oxygen. Okay, why? What they're saying is, why does it cost more energy to remove an electron from fluorine than it does from oxygen? Well, fluorine's got more protons in the nucleus, right? Let's read what they say. In both cases, the electron removed is from the same energy level, but fluorine has a greater effective nuclear charge. What did I tell you? You could use that to explain it. Due to one more proton in its nucleus, the electrons are held more tightly and thus take more energy to remove. Okay, question number C. Predict whether the first ionization energy of atomic xenon is greater, less than, or equal to the first ionization energy of fluorine. Justify your prediction. First ionization of xenon should be less than the first ionization energy to fluorine. To ionize the fluorine atom, an electron is removed from a 2p orbital. For a xenon atom, it's removed from a 5p orbital. Now, some people got panic about this because they're like, well, isn't xenon a noble gas? Yeah, but look at how much lower on the periodic table it is. The electrons are 1, 2, 3, 4, 3 or 4 levels further away from the nucleus. Remember how we said electrons that are way away from protons experience less effective nuclear charge, so it's easier to remove them, even though it's a noble gas. You know fluorine is not very good at giving away electrons. You know that because it's the Tyrannosaurus rex of atoms that wants to get electrons, not give them away. So anyway, going back to reading this again. To ionize xenon, the electron will be removed from 5p orbital. The 5p is a higher energy level and further away from the nucleus than 2p, hence it takes more energy to remove. Let's see, they go on with some more questions here. Now they ask some questions about drawing Lewis dot structures. That's chapter 8, and shapes and stuff like that. We'll come back to that when we review chapter 8. More chapter 7 stuff, a table of ionization energies on question 6 from 2007. Write that down. Question 6, 2007. Question 6, 2007, a great chapter 7 problem. Okay, element 2 has the, which element is the most metallic character? We didn't talk about that. Metallic things, what separates them? Well, there's this dividing line right here, remember? Anything to this side and over is a metal, except for some of these, like these guys here are semi-metals, okay, semi-metals. Aluminum is considered a metal, so it actually belongs over here too. Okay, metallic character increases to the left and down, becomes more metallic, meaning is that it's good at giving away electrons, it is a good conductor, it's malleable, it's ductile, things like that. These are nonmetals, and then we talked about some things like that as well. So you look at these things, these elements right here, and what you want to do is you want to find one with a low first ionization energy, because obviously things over here easily give away electrons. They're good metals. They're low ionization energies. So your low ionization energy right here is 496. Element 2 is the most metallic character. Metallic elements lose electrons when they become ions, and the element 2 requires the least amount of energy. Identify element 3. Explain your reasoning. Look at element 3. It goes from 738 to 1450 to 7,000. Oh my gosh, it takes a quantum leap. It also tells you up here that it shows the first 3 ionization energies for atoms of 4 elements from the 3rd period of the periodic table. Now you got to be a good looker on the periodic table, and you got to say from 4 elements from the 3rd period. That's the sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And you can see from element 3 here that it takes a quantum leap after it loses 2 electrons. Who, after losing 2 electrons, would look like a noble gas? Who, after losing 2 electrons, would look like a noble gas? Magnesium loses 1, it looks like sodium. Loses another one, it looks like neon. Oh, so it's probably magnesium, right? Magnesium, element 3, has a low first and second ionization energies relative to the third, indicating the element has 2 valence electrons, and then it has a noble gas core, and it's hard to remove. Write the complete electron configuration for element 3. So there's magnesium. What is the expected oxidation state for element 2? Well, element 2 right here, remember, you said it was a metal. It loses an electron, and then look, it has a really high ionization energy right here, so it's probably just going to lose 1 electron. It's probably, I'm just making a guess here, but probably one of these metals right here, because these guys give away 1 electron, and then they have a noble gas core after that. And lastly, what's the symbol for element 2? Oh, I guessed it, it's sodium. And then the neutral atom of which of the 4 elements has the smallest radius? Element 1. How would I know that? Well, element 1 right here would be the furthest to the right on the periodic table because it has ionization energies that are generally the highest going along. And since it's generally the highest over here, remember atomic radius increases as we go to the left and as we go down. And so element 1 would have the smallest atomic radius. I think I'm getting confused here because I've done too many problems here tonight. Let's go on to the next one. Can I come back to that one in just a second? Let me look at the neutral atom, which of the 4 elements has the smallest radius. Element 1. What is element 1? Did I identify it? I don't think I identified it at all. Let's go with its element 1 right now. We'll come back to that in a little while. Let's go on to this one. Account for each of the following observations in terms of atomic theory or quantum theory. Atomic size increases from sodium to chlorine across the periodic table. Here it asks you to describe it. This is 2006 Form B question 7. Oh my gosh, they want you to tell why the size decreases from sodium to chlorine. The size decreases from sodium to chlorine. Hey, I was just talking about this. The reason it decreases is because there are more protons in the nucleus. More effective nuclear charge is experienced by these guys. Boron commonly forms molecules of this type, BX3. Why does it do that? Well, boron right here has 3 valence electrons, right? So it's good at forming 3 bonds with things, even though that breaks the octet rule. Boron has 3 valence electrons, each of which can form a single covalent bond with X. The ionization energy of K is less than that of Na. Oh, it's asking you to explain this trend again right here. Here's Na, here's K. Well, K, of course, its electrons experience less effective nuclear charge because the electrons are further away from the nucleus. Its atomic size is bigger because atomic size goes up as you go down. And the electrons are further away from the nucleus, therefore they have less attraction. Each element it displays a unique gas phase emission spectrum. Let's read what they say about this one. Each element has a unique set of quantized energy states for its electrons because of its unique nuclear charge and unique electron configuration. As the electrons of an element absorb quanta of energy, they change to higher energy states and are excited. During de-excitation, energy is released as electromagnetic radiation as the electrons cascade to lower energy states. Each photon of the electromagnetic radiation associated with a specific wavelength, wavelength equals hc divided by E, a flux of which produces the lines of the emission spectrum. Wow, that was quite the explanation. Let's try another problem. This is question 8 from 2006. First of all, write the ground state electron configuration for Q. They say, suppose a stable element of number 119, symbol Q, has been discovered. 119, where would that go? 119, oh my goodness. Notice this element is 114, 115, 116, 117, 118. Where would that go? We'll go right here, 119. That would be right below francium. Can you see that? 119. You have to be able to count on the periodic table and say, oh, it would be an alkali metal. Oh, it's going to have properties like lithium, sodium, potassium, rubidium, cesium. It's going to explode when it's put in water. All right? Going to react, form some hydrogen. Write the ground state electron configuration, 8s1, because it would be in the 8th period, S group. Would Q be a metal or a nonmetal? It'd be a metal. On the basis of this, would Q have the largest atomic radius in the group? It would have the largest because, of course, atomic radius increases as you go down. What would be most likely charged? Positive 1. Write a balanced reaction of Q with water. Well, Q would react with water to form some H plus gas, right? And it would form a strong base because, of course, all of these are part of the B on the periodic table. And this strong base completely dissociates. Assume that Q reacts to form a carbonate compound. Write the reaction. It would be Q2CO3 because Q would be positive 1 and CO3 would be minus 2, and you crisscross those. Predict whether or not the compound would be soluble in water. I would say it would be because pretty much lithium, sodium, potassium, rubidium, and cesium, any of those, remember, group 1s are always soluble. Good question. Good question. That's making sure you know the trends and how to answer questions about those trends. Last one, 2009 question 6. 2009 question 6. Consider the chemical species S and S2 minus. Write the electron configuration for each. Look at this. You got to be able to write the electron configuration for something that's got a negative 2 charge. So it's got 2 more electrons than the other one. Notice they allow you to write the shorthand one if you want. Explain why the radius S minus 2. Explain why the radius of S minus 2 ion is larger than the radius of the S atom. Nuclear charge for both, the nuclear charge is the same for both species, but the 8 valence electrons in the sulfide ion experience a greater amount of electron-electron repulsion than do the 6 valence electrons in the neutral sulfur atom. This extra repulsion in the sulfide ion increases the average distance between the valence electrons, so the electron cloud around the sulfide has a greater radius. I think you could also say that the S minus 2 valence electrons, or ion electrons, experience less effective nuclear charge because there's more electrons than there are protons. Which of these 2 species would be attracted into a magnetic field? This one has to do with paired and unpaired electrons, being paramagnetic or diamagnetic. Let's read their answer. The sulfur atom would be attracted into a magnetic field. Sulfur has 2 unpaired p electrons. Remember, if they're unpaired, they're attracted into a magnetic field. This results in a net magnetic moment for the atom. The net magnetic moment would interact with an external magnetic field, causing a net attraction into the field. The sulfide ion would not be attracted to the magnetic field because all the electrons in the species are paired, meaning that their individual magnetic moments would cancel each other out. So if you went back up here and you wrote the electron orbital notation for it, the 3p right here for sulfur would be 1, 2, 3, 4, and you'd have 2 unpaired electrons. Whereas for the sulfide ion, there'd be 6 electrons, 1, 2, 3, 4, 5, 6. And you can see that they are paired. The unpaired electrons are things that allow it to be attracted into a magnetic field. You could just remember paired electrons, unpaired electrons give it magnetic properties, attraction to things. The S minus ion is isoelectronic with the argon atom. From which species, S2 minus or argon, is it easier to remove an electron? Explain. What does isoelectronic mean? Isoelectronic means the same electron configuration. And if you write the electron configuration for S minus or argon, just the outer part, remember that the 3s2 would have 2 electrons and the 3p6 would have 6 electrons in it. Okay, just like that. It requires less energy to remove an electron from a sulfide ion than from an argon atom. A valence electron in the sulfide ion is less attracted to the nucleus, a charge of plus 16, than a valence electron from the argon atom, because the argon atom argon atoms' electrons experience a greater effective nuclear charge. They have more protons in the nucleus. All right, good.